Hello and good afternoon to all of you. I hope all of you are doing well and all of you are in good health. In today's class, we will discuss some of the important storage fundamentals. To begin with, let us try to understand random access memory. Random access memory, which is also commonly called as RAM, is a memory device where the information is stored in a collection of tiny capacitors. A charged state of the capacitor is considered to be 1 and an uncharged state of the capacitor is considered to be 0. So there are millions of capacitors which would in turn represent sequence of zeros and ones for representing programming instruction and data. So RAM or random access memory is a type of memory where the information is stored in a set of tiny capacitors where the charged state of capacitor is considered to be 1 and an uncharged state of the capacitor is considered to be 0. So collection of such many tiny capacitors would create a representation of data and programming instructions in terms of zeros and ones. So at atomic level, these zeros and ones are called as bits. So every capacitor is capable of storing or representing a bit of information. Now likewise, hard disk. Hard disk, which is also commonly known as HDD, is a storage device where the bits pertaining to the data and the programming instructions are stored in magnetized disk. So if a line is magnetically attractive, it is considered as 0, and if it is magnetically repulsive, it's considered as 1. So magnetic attraction and repulsion, combination of such attraction and repulsion would represent zeros and ones that would eventually represent programming instruction and data that is stored in the hard drive. So again I repeat it, hard drive or HDD as it is called is a memory device where the data is stored or data and programming instructions are stored in magnetized disk, wherein if a line is magnetically attractive it is considered as 0 and if a line is magnetically repulsive it's considered as 1. So such sequence of attraction and repulsion would represent sequence of bits representing program instructions and data. Now likewise we have SDT, that is solid disk drive. It's also commonly known as SDD. So here the information is stored in a collection of tiny transistors. So a charged state is considered as 0 and an uncharged state is considered as 1. So here in case of SDD, in contrary to RAM, we use transistors where the charged state is considered to be 0 and the uncharged state is considered to be 1. So sequence of or a collection of tiny transistors representing zeros and ones is being used in order to represent the programming instruction and the data. Now here some of these technologies are volatile in nature and some of these technologies are non-volatile in nature. So for an example, since RAM depends on the technology of capacitors, so whenever the power is turned off, the capacitors are discharged. So RAM is a volatile piece of memory. So whenever data is stored in RAM, if the power supply goes down, then the content of the entire capacitors are flushed. So that's why RAM is not capable of retaining information that is stored in it once the power is turned off. But likewise, since the data is stored in hard drive and in case of SDD in a technology that is capable of retaining data, so these are examples of non-volatile memory. So some of these are volatile and some of these are non-volatile memory. So just to let you know. Now let us learn something about bit byte hierarchy. All of you know it. So bit byte hierarchy basically represents the way how we represent the way how the units in which the memory is represented in context to computer system. So we have the atomic representation of memory called as bit. So bit is the atomic representation of memory. So atomic representation of memory, that is atomic unit of memory. So a bit represents either 0 or 1. So one bit of information. So you can store either 0 or 1 in a bit. So for example, in case of a RAM, so you use capacitor to represent 1. In case of SDT, you use transistors to represent 0 or 1. In case of hard disk, you use magnetic repulsive or magnetic attractive as zeros and ones. So either of these technologies are capable of representing 0 or 1. So 0 or 1 is referred to as a bit. So bit is represented by small b, that represents the atomic unit of memory, that is either 0 or 1. Now the next unit that we have is called as a nibble. Nibble is a collection of 4 bits. Again, I'll repeat it. Nibble is a collection of 4 bits. Now next one you have is byte. So byte is represented by capital B. So byte is a collection of 8 bits. Again, I repeat it. Byte is a collection of 8 bits. So 8 bits make 1 byte. Now the next notable unit of memory is kilobyte. So kilobyte is represented by KB. Now normally in case of decimal system, we represent kilo by 10. So since computer systems are base 2 system, so the nearest value to kilo is 1024. So nearest value to 1000 in powers of 2 is 1024. So in case of base 2 system, kilo basically refers to 1024 because 1024 is the nearest value to 1000 in terms of kilo. So that is the way how we represent kilo in case of computer system, because computer systems are base 2 systems, right? So kilobyte is represented by KB and is equivalent to 1024 bytes. 1024 bytes. So that is the way how we represent kilobyte. So it's very important for all of us to understand, because in base 2 system the nearest value of kilo to 1000 is 1024. Now next one is megabyte. So megabyte is represented by MB. So 1024 kilobyte is equals to 1 megabyte. That is 1000 kilobyte or 1000 kilobyte or 1024 kilobyte is equals to 1 megabyte. Now likewise we have gigabyte. Gigabyte is represented by GB. So 1024 megabyte is equals to 1 gigabyte. So 1024 megabyte is equals to 1 gigabyte. Likewise you have terabyte. So terabyte is represented by TB. So 1024 gigabyte is equals to 1 terabyte. Again I repeat it. 1024 gigabyte is equals to 1 terabyte. Now likewise pentabyte. Pentabyte is represented by PB. So 1024 terabyte is equals to 1 pentabyte. Again I'll repeat it. 1024 terabyte is equals to 1 pentabyte. Now likewise you have exabyte. So 1024 pentabyte equals to 1 exabyte. Again I repeat it. 1024 pentabyte is equals to 1 exabyte. Now next we have zettabyte. So 1024 exabyte is equals to 1 zettabyte. Zettabyte is represented by ZB. So 1024 exabyte is equals to 1 zettabyte. Now likewise 1024 zettabyte is equals to 1 yottabyte. So yottabyte is represented by YB. So these are the various units in which you may have the memory represented. So you may have memory represented in terms of bit, you may have memory represented in terms of byte or kilobyte or megabyte or gigabyte, terabyte, petabyte, exabyte, zettabyte and yottabyte. So depending on the requirement of the system, you can organize the memory in any units. Now as discussed, there are two types of storage devices. You have volatile storage device and non-volatile storage device. So volatile storage device is a device wherein which is rather not capable of retaining its content when the power to the device is removed. Whereas non-volatile storage devices are devices which does not lose its content even when the power is removed. So it holds all the data when the power is removed. So it's capable of retaining this. So it basically implies in simplicity that it's capable of retaining whatever is stored in it. So depending upon the requirement, either you can have a volatile or non-volatile memory installed in your computer system. So now Then we have memory types and hierarchy. Now this is a very important representation that all of you need to understand. So as I've said, there are different types of memory in a computer system. So let us try to understand each of these memory types in a greater detail. So you have registers, you have cache, you have main memory, you have SSD, solid state disk, then you have hard disk, you have optical disks, you have magnetic disks. So these are all data storage devices. Now let us try to understand the significance of all of this. So registers are, as I've said, or as I've already discussed, and we'll be discussing in the subsequent slides as well. So registers are the onboard memory to which the central processing unit directly interacts. So it is a piece of memory where the programming instructions and the data that is used by the processor is stored. So since it's an onboard memory, we can have only limited number of cells or limited number of registers in CPU. So we have very less number of CPU registers, but it's a very high speed memory, and it's the only memory to which the CPU interacts. So register is in terms of performance. It's very high performance memory, right? Okay, but in context to size, it's relatively smaller in size compared to other memory. Now cache memory. Now cache, as I've said, is used in order to supplement the CPU registers. So cache will store frequently used set of instruction and data by the processor, and I'll again repeat it. So cache is used in order to supplement the CPU registers. Now there are different variants of cache. So you have L1 cache, you have L2 cache, you have L3 cache. In simplicity, you have internal cache and external cache. So internal cache is an onboard memory, whereas external cache is an offboard memory. So internal cache is used in order to supplement the CPU registers. In context to configuration, these are called as L1, L2 and L3 cache. So L1 cache is used in order to supplement the CPU registers, and L1 cache is generally it is an onboard memory, whereas L2 cache, it may be present in the memory, or it may be present in some other coprocessor, but it's used in order to supplement L1 cache. Now likewise, L3 cache is an off-boot memory which is used in order to supplement L1 and L2 cache. Now we'll come to that in detail, but for now just remember that there are two types of cache: internal cache and external cache. Internal cache, external cache, both are used in order to supplement the CPU registers. Both are used in order to store the programs and instructions that the CPU register requires, which will be further communicated to the processor in order to perform operations. So cache is also very high speed memory, but you can have cache of only limited size. Then you have main memory. So main memory is the program is the memory where all the program and the data that is required by the processor is kept. So main memory is the memory where the program and the data that is currently being used by the central processing unit is placed. Subsequently, as and when the processor requires it, it is transferred to cache and then to register, and then eventually the processor utilizes it. But whatever is required by the processor at a given point in time, that is present in the main memory. Now main memory is another use of the main memory is that main memory is an interface between all the other units. So whenever you want to store data that's being read from the environment through the I/O devices or input device, so that data has to first come to the main memory and then it can be stored in the secondary storage device. Or if any program from the secondary storage device is to be executed by the processor, so it has to be brought to the main memory first. So main memory actually acts as an intermediator between all the other units. So whatever data flow takes place in the system happens through the main memory. So that is the significance of main memory. So as I've said, whatever data flows through the system or is processed by the system has to go through the main memory. So no other units in the computer system has a direct interface with each other. It will happen through the main memory. So that is the importance of main memory. So the primary importance of main memory is that main memory is capable of hosting the programming instruction and data that is to be executed by the processor. and it acts as the interface between all the other units. So whenever whatever interaction takes place, it happens to the main memory. Then you have the secondary storage devices. You have solid state disk, you have hard disk, you have optical disk, and magnetic disk. So these are storage devices that use different technologies in order to store data onto it. So this are the various types of memory that you can have in a computer system. So we'll learn about each of these types of memory in greater detail. But you need to always know that which are the set of memory to which the processor interacts, which are the set of memory that are volatile, which are the set of memory that are non-volatile in nature, which are the types of memory that are on board, and which are the types of memory that are off board. So it's very important for all of us to know. So let us create a very simple representation. So these are the dots. So these are the colored dots that represents various memory types in the plot. So here we have a plot, right? So speed and cost. So just see, here it's a very simple plot where again along one of the axes we have size, and along the other dimension you have speed and cost. So register is in terms of cost, speed. It is a very expensive memory, and it's a very high speed memory, and you have very limited size to it, right? Then comes cache, right? So you have speed and cost versus size. So as the size grows, so the cost will also grow, and it's very high speed memory. Then comes main memory. Then you have solid state disk. Then you have hard disk. Then you have optical disk, and eventually you have magnetic tapes. So magnetic tapes are the slowest of the memory, inexpensive slowest of the memory, irrespective of the size. So from this plot we can understand that CPU is a very high speed memory, and it's very expensive when the size grows. Likewise, cache is relatively high speed and expensive with the increase in size. So likewise, you have main memory, solid state disk, hard disk, optical disk, and magnetic tape. So this is a very important representation that tries to represent the significance of the various types of memory that a computer system has in it, and what would be the expenditure in terms of investment, and what would be the performance in terms of speed. Now now we have a very simple hierarchical representation of the way how the data flows. So you have register, you have cache, then you have main memory, you have solid state disk, you have hard disk, you have optical disk, and eventually you have magnetic disk. So interaction takes place between registers and CPU registers and cache. Then cache interacts with main memory. Main memory interacts with other secondary storage devices like solid state disk, hard disk, optical disk, and magnetic disk. So you have a bidirectional data and instruction flow between the various storage devices that are there in a computer system. So this is a very important representation that all of us needs to understand, and we need to understand this plot as well, because this plot is a very important representation that shows the cost and speed versus size representation to various memory types. So again, I'll repeat it. So we have CPU registers, we have cache, we have main memory, we have solid state disks, we have hard disks, we have optical disk, and magnetic disks as different memory devices in a computer system. So out of all of this, registers are very high speed and very expensive memory. And with the increase in the size, the cost also increases exponentially. So that is what this particular graph tries to express. Now moving forward, now let us try to understand all of these memory in greater detail. So to start with, register. So register memory is the memory located in the CPU itself. So it's an onboard memory to which the processor directly interacts. So CPU registers are memory that are located in the CPU itself, and these are the memory to which the processor directly interacts. So it's the only memory to which the processor directly interacts. So it holds frequently used data, instruction, and memory address that are to be used by the CPU. So it holds frequently used data, instruction, and memory address that are to be used by the CPU. Now likewise, you have cache. Now cache is a supplementary memory that supplements CPU registers by temporarily storing frequently used instruction and data for quicker processing. So as I've already said, so cache memory is used as a supplementary memory that is capable of supplementing the CPU registers, and it temporarily stores frequently used instructions and data for quicker processing. Now likewise, you have different types of cache, as I've already said. So you have L1 cache, you have L2 cache, and you have L3 cache. Now L1 cache or primary cache is an extremely fast but relatively small memory, and it's usually embedded in the processor chip as CPU cache. So it's an onboard memory, right, that is capable of supplementing the CPU registers, and it's extremely fast, but it's relatively small. Now the next type of memory that you have is called as L2 cache. Now L2 cache or secondary cache, it is often more capacious than L1. So it is in size, it is always bigger than that of L1. So it's capable of storing more volume of data compared to that of L1. Now L2 cache may be embedded on the CPU. So it may be either placed in the CPU itself, or it may be placed on a separate chip or a coprocessor. So either of these two are likely. So L2 cache may be present in the processor itself, or it may be placed in some other chip or a coprocessor. But you need to understand that in case of L2 cache, it has a high speed alternative system bus connecting the cache and the CPU. So L2 cache has a very high speed CPU bus, alternative CPU bus that connects L2 cache with the CPU. So that's why it does not get slowed by traffic on the main system bus. So this is to be understood. So L2 cache is also called as a secondary cache. It may be present in the CPU itself, or it may be present in a coprocessor associated with the CPU. It's capable of supplementing the L1 cache, right? And definitely traffic will not be hampering the efficiency of L2 cache, because L2 cache has its own dedicated alternative high-speed system bus connected to it, which connects it to the CPU. So that is the purpose of L2 cache. Now L3 cache. Now L3 cache is an off-board memory that is developed in order to improve the capabilities of L1 and L2 cache, or improve the performance of L1 and L2 cache. So L1 and L2 cache are significantly faster than L3 cache, and generally L3 cache is L3 cache is double the size of the speed of RAM. So that is what's L3 cache. So L3 cache is an off-board memory that is used in order to supplement L1 and L2 cache, in order to enhance the performance of L1 and L2 cache. So this is what CPU register is. So CPU register is a memory that is in direct contact with the CPU central processing unit. It stores frequently used instruction and data, and in fact it is the only memory to which the CPU is connected. Then you have cache memory. Cache memory is also called as supplementary memory. It is used in order to supplement the CPU register, and it holds frequently used instruction and data. There are three different variants of cache: L1 cache, L2 cache, and L3 cache. L1 cache is an onboard memory that is it's very fast, but relatively smaller in size, and it's often placed in the processor itself. Then we have L2 cache. Now L2 cache is called as a secondary cache. It is more spacious than that of L1 cache. Now L2 cache may be embedded in the processor, or it may be placed in a separate chip or coprocessor associated with the processor. But in case of L2 cache, the traffic would not have an influence on the performance of L2 cache, because L2 cache has its own dedicated high-speed alternative channel or bus which connects it to the CPU for communicating data. Now likewise L3 cache. So L3 cache is used to supplement L1 and L2 cache, or to enhance the performance of L1 and L2 cache. So this is a very important concept that you need to remember. Now let's try to identify some of the advantages and disadvantages of cache memory. So advantages. So cache memory stores data for temporary use, consumes lesser access time, stores the program that can be executed within a short period of time. Now just see, cache memory, it's capable of storing data temporarily. It consumes lesser time in order to access it, because you have limited size. So to search for an element in a relatively smaller size will definitely take smaller amount of time. So it can store smaller programs that are to be executed. Now, one of the major disadvantages of cache is that cache memory has very limited capacity and it's very expensive. So, with the increase in the size of the cache, definitely the cost investment would come up, right? So, cache memory is it has a very limited capacity and it's very expensive. So, these are some of the advantages and disadvantages of cache memory. Now, let us try to understand the working of cache memory with the help of very simple schematic representation. So here, whenever a processor wants to access data, so whenever a processor wants to access data or instruction that it wants to execute, so first what it will do is it will search for presence of the instruction and data in the cache. If not found, then only it will go on to the main memory. So first what it will do is it will search for the address that is to be looked in the cache. If it is found in the cache, then it's drawn from the cache, or else it is looked for it in the main memory if the address is not found in the cache. So here we have the processor. So processor will provide the memory address from where the instruction and the data is to be fetched, or instruction or data is to be fetched. Now that address is simultaneously compared with the address values that are there in the cache. If it is found, then the data that is there in the corresponding address locations are drawn and supplied to the processor. If the address is not found in the cache, then what we do is we search for the address in the main memory and we try to draw the data or the instruction that's stored in the address and place supply it to the processor or the coprocessor. So that is the way how caching basically works. That is the way how caching basically reduces access time. Now here it said caching reduces access time. Definitely, whenever the size of the memory is relatively small, then the access time required will be definitely less. So this is to be understood. So it's easy to search for an element in an area of size 10 rather than searching for an element in an area of size, say for an example, 1 gigabyte. So that is the difference. So if the size is relatively small, the search time would be definitely less. So this is the way how caching works. So first we'll search for the presence of the address in the cache memory. If it is found in the cache memory, then we'll draw the data from there, or else we move on to the main memory. Now let us try to understand the next type of memory that is called as main memory. So the main memory stores the operating system, software applications and other information for central processing unit to have fast and direct access when needed to perform tasks. As I've already said, main memory is a type of memory that is capable of, or that is supposed to store programming instruction and the data that is to be executed by the central processing unit. Now, since there might be several programs that may have to be executed either on the demand of the system or on the demand of the user, so what we need to do is we need to have a very efficient algorithm that is capable of partitioning the memory into identifiable partitions where different partitions are assigned to different programs. So this is the way how main memory works. So main memory is a memory that stores operating system program, software applications and other informations that are required by the central processing unit. Now it's also called as random access because the CPU can go directly to any section of the main memory and does not have to go about the processor in a sequential order or the process in a sequential order. So it's also referred to as also random access because the central processing unit can go directly into any section of the main memory in order to access either instruction or data. Now the data and instruction required to be processed resides in the main memory. So this is very important. So all the data and instructions that are required by the central processing unit is to reside in the main memory. Now in addition to this description of main memory, it's also to be understood that main memory acts as an interface between all the other units that are there in the computer system. So any interaction that takes place in the computer system takes place through the main memory. So as I've said, if a data is to be stored that is being read by an input device, it has to go through main memory. If a program is to be bought from the secondary storage device and it's to be executed by the processor, it has to be brought to main memory. So main memory acts as an interface between all the other devices, all the other units that are there in the computer system. So this is the second importance of the main memory. So main memory stores operating system program and the application program and all the other relevant information that's required by the central processing unit in order to perform operation. It's also called as random access memory because CPU can go into any location in the main memory in order to fetch the data or instructions. Now next type of memory that we have is called as SSD, that is solid state disk. Now solid state disk is a type of memory that is capable of storing the data permanently. But here what we do not have is we do not have moving parts, in contrary to hard disks. So in case of hard disks you have magnetic disks that revolve, where line of magnetic attraction and magnetic repulsion is represents 0 or 1. So there we have mobile parts, but in case of SSD we do not have mobile parts. So here in case of SSD we do not have moving parts, so it gives a very big advantage that it's very fast, right? It has a faster access time, it generates less noise, it consumes low power, and it's highly reliable compared to that of hard disk. So solid state disk does not have any moving parts, right? It uses transistors in order to store data. So if it does not have any moving parts, then it has very less access time. So it has faster access time, it generates less noise, it's highly reliable, and it consumes low power. Now the next technology that we have is called as hard disk. So these are used for storing data information permanently. So CPU directly does not access this memory, instead they access via input-output routines through the main memory. So this is to be understood. So hard disk is used in order to store data and information permanently, but CPU cannot have a direct access to the hard drive. Instead the access happens through the main memory. Now the content of the secondary memory are first transferred to the main memory and then CPU can access. So this is what I was trying to refer to. So the content, any content that the processor wants to refer to, it has to be first brought into the main memory and then the CPU can access it. So these are different types of memory. So you have main memory where the operating system and the application program resides. It's also called as random memory because CPU can move on to can go on to any portion of the main memory and access instruction byte or data byte in order to perform operation. So in addition to this, main memory also acts as an interface between all the other units that are there in the computer system. So any interaction that takes place in the computer system happens to the main memory. Then we have solid state drive. So solid state drive, in contrary to hard disk, it does not have any moving parts. So it uses transistor technology, so it gives it an advantage. So it has a faster access time, it generates less noise, it's highly reliable, and it consumes lesser power. Now hard disk, in contrary to SSD, it has moving parts where information is stored over magnetized disks. Where patterns of magnetic repulsion, magnetic attraction is used in order to represent data. So it is considerably slower access time compared to that of SSD. It generates noise. It is less reliable compared to that of SSD, and generally it consumes greater power requirement because of the mobile parts. And the processor does not have direct access to hard drive, so any content that is to be accessed from the hard drive is to be brought to the main memory, and then the processor can utilize it. Now the next type of memory that you have is called as optical disks. An optical disk is an electronic data storage medium that is also referred to as optical disk. Optical storage, optical medium, optical disk drive which reads and writes data by using optical storage techniques and technologies. So here in case of optical drives we use the concept of bits and LANs. So bits and LANs are used in order to represent the bit sequence, either zeros and ones. So that's the way how the optics interprets zeros and ones that are stored in the optical disks. Then we have magnetic disks. So these are the slowest of the memory type. So it provides a compact, economical means of preserving and reproducing various forms of information that is there. So all of us, we have seen magnetic tapes that are capable of storing capable of storing information in terms of songs and videos and so on and so forth. So this is the least expensive of all the memory storage devices. So now here we have a very sound comparison of all the memory types. So here we have names of the memory types. So we have registers, we have cache, we have main memory, we have SSD, and we have magnetic disk or the hard disk. So typical size of register is less than 1 kilobyte. Typical size of cache is less than 16 megabyte. Typical size of main memory is less than 64 gigabyte. Typical size of solid state disk is less than 1 terabyte, and typical size of magnetic disk is less than 10 terabyte. So this is in terms of size. Now implementation technology. So registers, so custom memory with multiple ports, CMOS. In case of cache, one on-chip or off-chip CMOS. Then in case of main memory you have SRAM, CMOS SRAM. In case of solid state disk you have flash memory. In case of magnetic disk you have hard disk or magnetized disks. So these are the technologies that are used. Now access time in terms of nanoseconds. So in case of register the access time is around 0.25 to 0.5 nanoseconds. So as you see, the access time is very less. So it's 0.25 to 0.5 nanoseconds. In case of cache, it is 0.5 to 25 nanoseconds. In case of main memory, it is 80 to 250 nanoseconds. In case of solid state disk, it's 25,000 to 50,000 nanoseconds. And in case of magnetic disk, it is around 50 lakh nanoseconds. So access time. So just see how small the access time is in case of registers and how big the access time is in case of magnetic disks. So this is to be understood, right? So the more efficient of the memory type, lesser will be the access time. So this is a very important quantitative measure. So in case of register, access time is 0.25 to 0.5 nanosecond. In case of cache, it is 0.5 to 25 nanoseconds. In case of main memory, it is from 80 to 250 nanoseconds. In case solid state disk, it is 25 to 50,000 nanoseconds. And in case of magnetic disk, it's around 50 lakh nanoseconds. Now bandwidth, that is the data transfer, that is megabytes per second. So it is around 20,000 to 1 lakh megabytes per second in case of register. Just see the speed at which the data is being transferred. Now in case of cache, it is 5,000 to 10,000 nanoseconds. In case of main memory, it is 1,000 to 5,000 megabytes per second. In case of solid state disk, it is around 500 megabytes per second. In case of magnetic disk, it's around 20 to 150 megabytes per second. Now just see, this is the rate at which the data is being transferred from the various memory types. So if you consider access time and bandwidth, registers are the best types of memory that you can have, and magnetic disks are the worst type of memory that you can have, right? Because the access time in case of register is the lowest and the bandwidth is the highest. So we want lesser access time with greater speed of data transfer. Now registers are managed by compilers, cache is hardware, Main memory is managed by operating system. Solid state disk is again managed by operating system, and magnetic disk is again managed by operating system. Now here, registers are backed by or supplemented by. What you mean by is backed by or supplemented by. So registers, as we already know, is supplemented by cache. Cache is supplemented by main memory. Main memory is supplemented by disk. Solid state disk is also supplemented by disk, and magnetic disk is also supplemented by disk. So this is a very neat representation of various memory types that the computer system has. So I've taken it from an author. So I've taken it from Galvin and Gain. So it's a published article. So so I took it from them because it gives a very neat and a clean representation of various types of memory, and tries to compare across different parameters. So you have size, technology, access time, bandwidth, managed by and backed by or supplemented by as parameters for comparing the different memory types. So this is a very neat representation that tries to compare different types of computer memory or memory that may be there in computer system. Now, in today's class, so what we have learned about is we have learned about the fundamentals of computer memory. We have learned about the technologies that are used in RAM, hard disk, and solid state disk. So we have learned that RAM uses capacitors, hard disk uses magnetized disks, and solid state disks it uses transistors. So different states of either capacitor or magnetic lines or transistors are used in order to represent zeros and ones in case of RAM, hard disk, and solid state disk respectively. And then we came across bit-byte hierarchy, where we learned that the atomic representation of memory is done in terms of bits. So bit either represents 0 or 1. So this is the atomic unit of memory. Then we came across byte. Then we came across kilobyte, megabyte, gigabyte, terabyte, petabyte, exabyte, zettabyte, yottabyte, and learned about what would be the size in terms of its constituent unit representation. We also learned about the shortened notation for each of these identifiable units, and then we came across what a distinction between volatile and non-volatile memory, where we learned that volatile memory is a memory that is not capable of retaining the content once the power is turned off. In contrary, non-volatile memory is capable of retaining the content. So then we learned about memory types and hierarchy, where we created a plot between speed, cost, and size. So with the increase in size, we saw there's an exponential increase in cost. So we also learned that registers are very high speed memory, and magnetic tapes are relatively low speed and inexpensive memory. And then we learned about the way how the data flows and the way how the supplement or backed by is done. So cache and register interacts, cache and main memory interacts, main memory and solid state disk interacts, so and so forth. The other disks, they do interact with each other. Then we learned about the memory types in greater detail, where we learned about the importance of CPU register. Then we learned about the importance of cache memory. We learned about different types of cache. We learned about advantages and disadvantages of cache. We learned how cache technology works, and then we moved on to the importance and significance of main memory, then solid state disks, and then we moved on to hard drive, and then eventually we discussed optical disk and magnetic tapes. Then we made a comparative. Then we learned about the comparisons between various types of memory by taking into consideration size, implementation technology, access time, bandwidth, managed by and supplemented by as a basis for comparison or comparison measure. So we'll call it today. Thank you very much.